Limit as b goes to infinity, 1 to b, d dx of ln x over x dx. Now what?
Can you take out the dx?
What does the fundamental theorem of calculus tell us?
It's just ln x over x.
Correct. When you integrate the derivative, where do you get back to? The function itself. So what do you end up with? The limit as b goes to infinity of ln x over x from 1 to b. Exactly. Great. So what are you going to end up with? You're going to end up with ln of b. Well, hold on. Let me move this over here. The limit as b goes to infinity of what? ln b over b minus what? 1 over 1. What is ln of 1?
0.
It is 0. Nice. So this thing is 0. So now you need to analyze this. The limit as b goes to infinity of ln b over b. How do you figure that limit out? Yeah? L'Hopital's rule. Exactly. You have to use L'Hopital's rule because you can't just say big and bigger or biggish, right? You need an actual rule here. You can apply L'Hopital's rule y on this one. It's a limit of indeterminate form. What does the numerator go to? No. What does the denominator go to? This is infinity over infinity. This is an indeterminate form. So what can you do? You do this little h thing. You do the derivative of the top and bottom. It's the same thing. So what's the derivative of ln b? 1 over b all over 1. What does that go to? 0. Correct. You do not the quotient rule. You do the derivative of the top over the derivative of the bottom. That limit is equal to the limit of the other one. They're not equal expressions, but the limit, they go to the same place. That goes to 0. What?
Why do they go to the same place?
We don't prove L'Hopital's rule in this class, but that's a great question to ask. You could do that sophomore or junior college in a class called real analysis. Really cool question, but the success of this problem completely revolves around seeing a really cool substitution you can make. First realization is what types of numbers are a and b in that expression? They're constants, right? They're not variables. Here's the cool substitution. You might have looked it up and you might have seen it already. If you just pick a letter, and we'll call it t because that's the letter they use in the book. If we let t equal x minus a over the square root of b, if we do that, something really nice happens. Watch. This is really cool. If that's the case, remember a and b are constants, right?
Wait, then you just stop.
What is dt? Remember a and b are constants. Someone tell me what dt is going to be equal to.
1 over...
I'll give you a hint. This is 1 over root b x minus a over root b. So what's dt going to be? Dx, right? So what does dx equal?
Square root of b
Dt. Ah, so let's substitute now. What does this become? From e to the what power? Negative t squared. And instead of dx, what do I write? The square root of b dt. What about the limits of integration? These are x values right here. So what do the limits of integration become? Because every time you do substitution, you at least have to think about changing the limits of integration. What happens when you plug infinity in for x? Can you change something going to an arbitrarily large number by subtracting or dividing by a finite number? No. So what do the limits of integration stay? Oh, look at that. Negative infinity to infinity. What can I factor out of this thing? Y. Constant. Very good. So we have this right here. Do we know what this equals? Oh, look. What does this tell us? What does it tell you right there? The integral from does it matter what we call the variable? No, it doesn't. Yep. Square root of b, square root of pi, so you can do the square root of b pi. Yay. This right here is not something I would expect you to do. If I gave this question to you, I would give you this. I'd be like, hint, let t equal that. Because even with that knowledge, it's still a little tricky, right? But if you don't do that substitution, the way you would normally figure this out is you would play around with a ton of different substitutions trying to find something. The big hint is they're giving you this. So how do you turn this into this? You might square that out and try some weird thing. But if you start here, it's pretty clean. This is a great example of just because the algebra, the work, is not very complicated, does that mean it's an easy problem to solve? No, no. Just because it's easy to understand a solution doesn't mean that the solution was easy to find. Here's another example. You ready? I just multiplied two 3-digit numbers together, and I got the number 62,809. What are the two 3-digit numbers? That's an insanely hard question to answer. Factoring is hard, right? But if I gave you the two 3-digit numbers, could you check it really easily? Yeah. There are lots of operations that are easy one way and really, really hard the other way. Similarly, this is really easy once you have the key, but the key is really hard to see. Main lesson, don't assume that things are easy. You have to, this is one that you have to remember from last year, because you did differentials like this. When it says show the solution, show that that is a solution, it gives you this differential equation, which is any equation that has a rate of change in it. When it says find a solution, can someone tell me really simply what it's asking you to do effectively? Without using a synonym for solution. What do you do? One word. What'd you say? Integrate. It's asking you to integrate that thing. That's what it's asking you to do. It's asking you to do a few steps. It takes a few steps, but find the function whose derivative gives you that. How do you go about doing that? There's a first step. You have to get all the y's on one side. Specifically, you need the dy's to be attached to y's. And where do you want the dt's to be? Or not y, right? Do you understand what I'm saying there? Not y. So mathematically, what should I do first? Isolate y? Nah, not isolate y actually. Divide by? Yeah, and maybe multiply by dt. So you end up with dy over y minus a is equal to k dt. Now what can you do? You can integrate now. What did we just do? Does anybody remember what this is called? It begins with an S. Separation of variables. This is important. So now we can differentiate. If I differentiate the left, what does the left become? 左右上下, right? Equals what? KT plus some constant. I'll call it C1. Okay. Now what do we have to do? Nope. Careful. Now what do we have to do? It's asking for y equals. So what do we have to do? So isolate y. So that's going to be e to the kt plus c1 is equal to this. I don't really like those absolute values. You know it's going to be positive. Can someone tell me why? What's the left? E to a power is always what? Always positive. So what can you drop? Goes away. You know it's going to be positive. It has to be. So then what do you add to both sides? So you get y is equal to e to the kt plus c1 plus a. Doesn't match exactly what you want. You need to remember your exponent rules. This is the same thing as y equals e to the kt times e to the c1 plus a. And what you can do here is, the reason I said c1 is I'm just going to call this right here. I'm going to call this thing, instead of calling it e to the c1, I'm just going to call it what? Like c2. The reason I want c1 and c2 is that you will do integrals later in life where you're going to have to do lots of constant manipulation. And this is a really great thing to do, but you need to keep track of where your constants are coming from. So in this case, you end up with c2 e to the kt plus a. This work right here, any idea how much this kind of work would be worth on an AP question? 4, usually. This is 4. This, I think, is the best return on investment of any question on the AP exam. You usually get 1 point for separation of variables, then you get 1 for doing the integration, and then you get 1 for isolating y, and then usually 1 for like something. It's either 3 or 4 points. When you see differentials, you should get really happy because it's the best use of your time on the AP exam. Look at this. Nice and clean, you're done. Here's the tripwire, though, that kind of detonates you if you don't do. If you don't separate variables, you get a 0 out of 4 on this. It specifically says like 0 out of 4 if you don't separate variables. If you don't separate variables, all of this cascade can go wrong. But this is absolutely something you can see on the AP exam. Absolutely. Condition, what can you do? So let's say I dropped a buoy, let's say right here. It kind of looks like the buoy's going to go maybe like this. But that's because I started there. But let's say I started here. What does that look like? Kind of looks like maybe this. The point is, you don't get a trajectory, you don't get a path unless you have a point to start with. Kind of makes sense? Do you remember this? These are called initial conditions. This represents one particular solution. One particular solution. So, one thing you could be asked to do is identify a slope field based on the equation that they give you. Does anybody remember doing this last year?
No.
So, the way you don't do this is you try to generate the entire slope field manually. You do this by elimination. Let's look at this differential. I'm going to ask you one simple question about it. Can you tell me one interesting place on this slope field? Where does something interesting happen? What'd you say, Michael? You said it. What did you say? No, we're not solving this. When x equals y. Can you tell me why is it interesting when x equals y? It doesn't exist, right? On a slope field, how do you notarize doesn't exist? You don't draw anything, or what are you going to see? When x and y are really close together, what are you going to see on this graph? No, they're all line segments. What are you going to see? If x is really close to y on this thing, you're going to see a really steep line. Something with an infinitely steep sign. So let's graph y equals x on all of these. Y equals x. What does that look like? Y equals x, y equals x, and y equals x. So what do we know has to happen on that line? It shouldn't exist or be really steep. The slope doesn't exist or should be really, really steep. Because do we have any idea about the exact values of where these lines are? No, we don't. It's all an approximation. So you eliminate the things that are definitely not going to match. So let's zoom in here. Let's take a look here. What do you notice about the slopes on y equals x right here? They're all flat, right? That looks like 0. So this one probably isn't it, right? What about this one right here? Oh, they're really, really steep, right? It might be, right? And what about this one right here? But some of them aren't, though, right? It changes. So this one probably isn't it, too. So right now, it really looks like B is it, right? Let's try to get more verification. Look at the numerator of this fraction. What's the numerator tell us? When y equals negative x, what happens? It's 0. So what does that line look like? Like this. Is that slope 0? No. What about this one right here? Yeah, it does look like it. And what about this one right here? No. So therefore, if you had to pick one, which one do you pick? You pick B. Do it by elimination. Or find lines like this, which is part of elimination. I didn't mean or. You could pick specific points, but I like looking for the interesting things that are happening and looking for the general behavior. Or you could pick specific values. You could say, what's going on at 1, 1? Well, it's undefined. We'll look at 1, 1 in each case. The problem is, though, do we have the actual, are there any, scale to this? No, you don't have a scale, so you have to do it in a little bit more general of a way. On the AP exam, do they ever have you graph slope fields like this dense by hand? No. It takes forever, right? Could you be expected to graph a slope field? Yes. Usually, though, the slope field is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. I'm sure they did. It's very, very common. But at most, it's 16 points. And here's the thing. Do you have to sit there with a compass and be like, it's 45 degrees or it's 52 degrees? No. They're looking for 0, positive slope, negative slope, or straight up and down. That's all they're looking for. That's all they're looking for. You just have to do them carefully. You just have to do them carefully. So you might get, for example, y prime equals x plus y. How would you go about drawing that slope field? Well, they'll give you, they actually give you the dots. I'm trying to erase all these dots, it's kind of annoying. Yes. It goes through the dots. So usually you would get values, and it would be like, I don't know, like 1, 2, 3, I'll do one that's even bigger. And what do you have to do at each of these dots? Calculate the slope, and then what do you draw at each dot? That correlate to that value. So it's x plus y. So for example, at 0, 0, it's going to be 0. And then it's going to be 1, and then it's going to be 2, right? And then it's going to be -1 and -2.
Yeah, I feel like this is our exact.
This is a really, really, really common function, right? The point is, just do it carefully. Just do it carefully. Just do it carefully. There are functions, programs for your calculator that'll help you, right? Don't just rely on those. Again, what are the only two things you absolutely need to be able to do in your calculator for the AP exam? That's it. That's the only thing you have to do. Don't try to think you're going to get loaded up on programs and use them. There's a reason why they give you lots more time on the calculator part. It's not because it's harder per question. People tend to go a lot slower, significantly slower when they have the aid of a calculator. They tend to be less confident and overly check their work. It's true. These first slope fields right here, like here's an ocean current. If we wanted to use this slope field to estimate where we would go, if I picked a certain point, you'd start here, maybe go that far, and then start curving. You keep on evaluating where you're going based on where you go next. So, what does this look like mathematically? What does this look like mathematically as a process? Well, the first thing I will tell you is, when you do these, you need to take it slow and steady, because simple, small mistakes have huge cascading impacts. So what I mean by this is, we're going to start at one point, and then to decide which direction we're going to go, we're going to use the given differential, and it's going to say, okay, go that way. And then we're going to get to this point, and then we're going to use the differential equation again, and then it's going to say, okay, go this way. Then we're going to get to this point, and it's going to say, okay, go this way. So what do we end up with? We end up with a path. The function itself might look like this, but we have an approximation based on successive estimates as to where to go. The only things you need are, you need a differential equation, you need a starting point, and you need a delta x. The differential equation is the thing that tells you what direction to go in, given any xy coordinate pair. You have to have a point to start at. And then what is the delta x? Why do you need a delta x? Look at these segments. The delta x is how far over do we go each time we take a step. You kind of see what's going on here? The smaller, the more accurate, exactly. So if we took really, 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 really small delta x's, would our estimate would become more accurate? Sure. But we need to balance usability and accuracy. Yes, the smaller the delta x is, the more accurate it will be, but it'll be a lot harder to calculate because you'll be dealing with teeny tiny numbers. So you'll go in really slowly. Every time you make a move, you go really small. So these are the kinds of charts you're going to be figuring out or filling in. So take a look at this. It says, use Euler's method for dy dx equals y. So did that give us a really nice differential equation? Yes. Start with the point 0, 1. So if I'm starting this chart right here, do we have a starting value? Yes. So can we fill that in? Sure can. So what's that first value going to be right there for y? It tells us what that first value is for y. What is it? 1. We know our first value is 1. Are you with me so far? So we want to know, where are we after we go delta x to the right? Well, every time you go delta x to the right, you go delta y up, and this is your slope, right? You know that slope is equal to delta y over delta x. So what does delta y equal to? M times delta x. M is the slope, right? So if we want to find out delta y, what do we need? The slope times the delta x. What is delta x? It told us to use what? 0.1. And what was the slope? How do we figure out the slope if we're at the point 0, 1? How do we find out the slope? dy dx is equal to y. So the slope in this case is 1. So what is delta y going to equal in this case? 0.01. Exactly. 0.1, sorry. So that's our delta y. So we were at this point, but now the point goes up by 0.1. So what's our new y value? Exactly. It's going to be 1.1. So what do we do again? The same thing. What's our new point? What are we now at? What's the P1 point? No, the new P1 point is 0.1, comma 1.1. I understand what you're saying. So we need to do the same thing. What's the new slope going to be? 1.1 is the new slope. What's the delta x stay? 0.1. So what do we end up with? 0.11. So if I want the next, what's this value right here? 1 point what? 21. How did you get that? Delta y to the last y value. You added 0.11 to this, and you got that right there. You with me so far? How far could we do this for? We could keep going, right? We could keep going. On the AP exam, the farthest I've ever seen any question asked is like 3 of them. Like, this is as far. Because does it get kind of repetitive? And is it really easy to make some sort of mistake? Absolutely. It's really easy. So you might also, for example, you might also want to know what the true values are. So let's do, yeah, we could do the true values. What do you need in order to find the true value of the function? The equation, right? Well, let's see if we can find the equation. We know that, is this a relatively nice one? Yeah. So that tells us dy over y is equal to dx. So what can we do to both sides? Integrate. And what do we end up with? ln of y is equal to, not e, why do I write e? X plus c1. So e to the x plus c1 is equal to what? Y. So y is equal to some c2 times e to the x. Can we solve for the c2?
Yes.
Because we have what? What is this called? Initial condition. Yeah. So we know when x is 0, y is 1. So we have 1 is equal to c2 e to the 0. So what does c2 have to be? 1. So we know it's actually the function y equals e to the. It's kind of cool. So there are common differentials. So if you do, you will take, many of you will take a differential equations class in college. dy dx, you'll see a lot. dy dx equaling y is e to the x. Kind of cool. So what would we also need now if we wanted the true value? We now know it's y equals e to the x. But what do you really need? Yeah. So at the first point here, you're plugging in what for x? 0. So it's e to the 0. What is that? Hey, so we agree right now. It's perfectly accurate. Nice. Well, it should be because it's starting at the same point. What's the next one? E to the 0.1. So if you do e to the 0.1 on your calculator, can someone do that for me? Just give me it to 3 decimal places. E to the 0.1. What is that? 105. And someone do e to the 0.2. I think it's 1.22 something. Yeah. So take a look. It should be the same because it's stapled to that point. That's the initial condition. And then it's 1.1, 1.10. Oh, okay. It's roughly the same, right? It's roughly the same. So this is a way of estimating the path without integrating. You will see in your book this statement on the error of Euler's method. I've never seen it mentioned in the AP exam, so you can do this. I just wanted you to feel good about being able to do this. Yeah, I've never seen the error of Euler's ever asked about. I've never seen it ever asked about in every AP test I've ever seen. Probably, but who knows?